attending remote. I was just interrupted by the recording. Sorry, let me get that started again. So yeah, thanks everybody for attending. This is the third talk of the seminar series today. So it's an honor to introduce Professor Anupam Chattopadhyay. So that's a very difficult last name that I learned to pronounce when we were colleagues in Aachen. So Anupam studied in Jadavpur, then he did a master in Lugano in Switzerland, where actually I met him as well, because I did the master's also there. And then he went and did his PhD at the RWTH Aachen, where I also did my PhD. So we go way back. Now he's a professor at NTU in Singapore. He does research on application-specific structured net processors, and as some of you already heard, also in emerging technologies. And yeah, so I'm very happy to listen to your presentation, and just go ahead.
Yeah, thanks, Geronimo. So I will just, we need to get out and log into the meeting again because there is some Zoom permissions for sharing the screen. Okay.
Okay. Yeah.
Okay.
Yeah. That happens
Yeah.
if you haven't done it before. Yeah.
Yeah. Can you see this now?
Yes.
Yep.
Yeah. Okay. Let's just work. Okay. So, hello everyone, and thanks Geronimo for introducing me, and thanks Shatlia for organizing this together with Geronimo. It's always very interesting to connect to the like-minded people looking into the problems with cyber-physical systems. And today I will give an overview of the research that we are doing in this area for cyber-physical systems and the kind of security issues that we are facing there. So I try to introduce some concepts that we have been working on lately called secure by design. So to introduce myself, I did my bachelor's in India in 2000, followed by master's and PhD that Geronimo already mentioned. During PhD, I was working on partially reconfigurable processors. And this is an idea that found quite some interest in industry, and this tool that we developed was commercialized through Lasatech, which was acquired by cair, and eventually Synopsys purchased it. And then I spent a couple of years to work with this tool in a startup based in India, followed by a junior professorship in Germany from 2010 to 2014. And then I moved to Singapore in 2014, working on emerging technologies, electronic design, automation, bioinformatics, and all of this is somehow also connected with security and embedded systems. So jumping to the topic, so when I look into the research areas that we are working on, I try to visualize that in form of research wings, where we have 4 quadrants: algorithm, technology, automation, and system. So everything that we are thinking from the mathematical standpoint and the ideas in the application level, this is captured in the algorithm quadrant, which we eventually need to fabricate and map onto some kind of technology. So in order to take this algorithm to the technology, we take help of the automation, and we use various kind of systems, what we call a system architecture or system on chips, to realize this algorithm, to map the algorithm. So we touch upon different flavors of the research in algorithm. Like during my PhD, I started working on wireless communication because my supervisor, he was specializing in that area, where we were design automation flows for wireless communication so that we can map onto application-specific processors. And lately, I found a lot of interest, and there is a lot of research funding and open research problems in the area of security, of course, artificial intelligence, neural networks, machine learning, and biology also. So no one can overstate the importance of biology given the current situation that we are in. And so with all the restrictions on travel and resurgence of this new viruses. So when coming to the technology, I did work on, of course, CMOS technology nodes, advanced CMOS technology, and the corresponding problems that it came up with, like reliability and yield, approximate computing, And then I found some interesting technologies that are stretching the limits of traditional system architectures, like in-memory computing enabled by memristors or resistive RAMs, and then a completely new design paradigm being introduced by quantum computing technologies. There are systems architectures that I worked on, stemming from the building blocks like ASIC, coarse-grained reconfigurable architectures, partially deconfigurable processors, all of which are put together in a heterogeneous system on chip. And of course, to manage this complexity of the technology mapping or the system architecture design, I did participate in a lot of design automation flows, starting from high-level synthesis for ASIC or ASIC down to technology mapping for emerging technologies. So in the talk today, I will cover a bit of all these topics, and the focus is on where we stand in terms of the security of cyber physical systems or Internet of Things, and what we can do and what we are doing at NTU in order to get the security in place that we need. So we visualize the cyber physical systems or IoT that is enabling a lot of paradigms, what we say as of course, there was cloud computing, and then we have fog computing and edge computing. But what is there underneath? So one important thing to understand is that there is no stopping in the number of IoT devices and the gathering of data that we can in order to improve the efficiency of various kinds of systems. So we will have in near future 20.4 billion IoT devices, which means that there is a huge sensing or actuation layer, and the sensing is happening from biological, optical, acoustic. So all these small sensor nodes are sprinkled around us, and it will be growing more and more in future in order to better sense the environment and make useful decisions. But whatever we are sensing here, even if it's an internet connected, but there must be something which is providing the connectivity, and that is the communication layer, where we can have something ranging from ZigBee to 5G. We can have something local, like wireless area networks, Ethernet, or something which is more specific to a domain, like industrial plants having Modbus or automotives having CAN bus. So these communications enable us to collect the data and send it to a data center or fog computing scenario or a cloud computing framework. This whole setup is eventually improving the productivity, efficiency, the quality of service for traffic infrastructures, healthcare, autonomous vehicle, and this list is actually growing. So whatever we see now, let's say manufacturing, with the help of the CPS and IoT, what we are going to achieve is smart manufacturing, remote manufacturing. Instead of autonomous vehicle, we can say, okay, it's a internet connected smart autonomous vehicle. So it's making its own decisioning. So this is what we are looking forward to in the future. So I just go through a few simple examples and where the connectivity can lead to, and this is already reality. There are commercial offerings where you can have a smart home, which is full of devices. And these devices, they have their own access control protocols, and they have their own connectivities, which can be monitored through a communication, say, base station or a broadband communication portfolio that can look into these individual devices, and you can remotely monitor, you can remotely control what would be the current status of a particular infotainment device or the current conditioning of light. So this is what we are looking for, and this is what is already there, offered by many companies. So connected automotive and smart autonomous vehicle, this is already a rage, and we see there are major companies which are pushing ahead with the ideas that a car can have a very smart connectivity with lots of external devices. There can be car-to-car communication, there can be car-to-infrastructure communication, and of course there is a car-to-cloud setup. The in-vehicle network is also becoming more and more smart. So there is a major transition happening from traditional so purely mechanical and a bit of mechatronics devices to more digitization of this in-vehicle network. Smart health is another big area where we see a lot of push coming from not only the healthcare part, but people are also trying to realize that body can be used as a communication media. So there is a body sensor network, body area network, which is running in coordination with an automated medication. So if you're wearing some smart health devices, then you don't need to visit a doctor often. And as needed, it will be accurately monitoring your individual vital parameters and giving the medication as needed. So of course, this is connected with the same sensor gateway going to a cloud database and diagnostics that running on a remote server. So if you look into the layers of communication that we learned in our textbook, so from CPS and IoT layers, so this is the traditional OSI protocol layer, where we have the physical layer, MAC and network layer. And right now there is a lot of discussion going on how this layer should be adapted in order to fit into the IoT. Now, when we talk about the IoT, we use a very general terminology. It's Internet of Things. But if we talk with the different domains, that the IoT for Industry 4.0, or IoT for smart health, IoT for automotive, each of these domains have their own requirements and constraints. So accordingly, they need to customize the corresponding perception layer or the transport layer, computing layer. So transport layer is where it is using the traditional OSI backbone, but on top, there could be many more layers that can be coming in. And now I have just sprinkled some simple attacks that are already possible with these individual layers. And there we start having an idea where we are leading to. So the more connectivity that we are allowing and more automation and autonomous decisioning at individual layers that we are planning to support, they are opening up what we call as new attack surfaces. So in the physical layer, MAC layer, and network layer, there was already the possibility of denial of service, man-in-the-middle attack, IP spoofing. Now, on top of this, when we are talking about the perception layer, then there could be an RFID tag collision, a forgery, sensor spoofing. For a transport layer, apart from this, it could be an air gap attack. For the computing layer, of course, it's running on a cloud, so there can be malware, side channel attack, hardware Trojan attacks. For the application layer, it could be privilege escalation. So all these attacks that I'm mentioning here has been demonstrated for many different application scenarios. And what we are now facing is a clear battlefront between how much productivity, how much efficiency improvement we want to do with the help of CPS IoT, and how do we preserve the basic requirements of security and privacy. And this is quite critical because the applications that we are imagining, ranging from smart home, autonomous vehicle, or smart healthcare, all these have the capability to not only disrupt the service, but to affect human life. So this is of paramount importance. Now, there is a lot of discussion that goes on when we talk about the security and cybersecurity attacks at the ground level from cryptography. Now, cryptography is the art of securing things or achieving privacy. And there is a lot of research that happens in the cryptographic domain where people try to design new crypto ciphers and new crypto analysis techniques in order to make the ciphers more robust. So the question is, does all this analysis and cipher design really lead to some system level security enhancement, or can we translate, let's say, an attack from a cryptography to a system? So this is something that we have to keep a tab on because there are new developments that happens in cryptography. For example, the side channel leakage. This is a relatively new development, although there is a work that is happening over last 2 decades. It started around 2000. And even with this 20 years of work, a lot of attack has been demonstrated at the cipher level, but still the people who are working at the system design level, they are not really familiar with and not really defending all possible side channel attacks that we see there. And sometimes these attacks that we know are not really the complete list of attacks, because there is always a new side channel attack that keeps on emerging. The side channel attack that can happen because of a laser fault, because of a trace buffer that is there inside a processor, or there could be an attack that is enabled because we are moving to a new technology. So far the technology that we were using is CMOS. When we move to ReRAM or STT-RAM, some new attack can happen which we did not imagine before. So now from the system level security viewpoint, there are attacks that can happen in smart grid or unmanned aerial vehicle. And these attacks, although these are pretty simple, and I will discuss this particular attack that we conducted in the lab scenario, they are not really uh, in public knowledge for various reasons. So there are commercial designs and systems that you can buy from the market, which looks very straightforward to attack and violate the security and privacy restrictions that they come with. So for example, this is a commercial drone that we bought from the market, and it can be used for many different purposes, like delivering a letter or delivering a medicine, or even doing some kind of reconnaissance or survey over a region. And for this particular drone, it comes with a built-in GPS. Now, what this GPS does is it tells this drone for this area in which the drone is actually sold, where you can fly and where you cannot fly. So it has a restricted no-fly zone that is built in inside the UAV. And not only the zones, it can also consider putting a constraint on how high you can fly. Because if you are flying beyond a certain height, then it will of course clash with aeroplanes, and it will create some damage in the air traffic control system. So in order to protect from this, all the UAVs and drones, they come with a built-in map. And it also has a GPS receiver. So whenever it is going to a region and it is finding that it is in a wrong area, it will simply stop operating. Now what you see here is this lab set. It's a GPS recorder and GPS player. Although this looks like a bulky device, one can buy from the market a very simple small chip that can record and play the GPS. So we did this for the experiment purpose. We took this lab set device into a very different zone, and then we recorded the GPS signal at that zone. Then we came and started playing the GPS while we turned it on. So although this particular drone was in a safe zone where it should be flying and no problem, but due to this GPS playing in front of it, it recorded itself to be in a no-fly zone and it could not take off. So this is a very simple example of GPS spoofing. So that means that we are now relying on this GPS positioning for so many different kinds of activities. And with a simple device like this one, where it could be a Trojan drone, it could be a malicious drone flying close to it and starts playing the GPS, it can be fooled. And this is problematic because when we are talking about the commercial GPS signals, they don't come with the encryption layer. So there are some proposals that are emerging now, but as of now, you can spoof the GPS. So that is one example that we tried in our lab. Another example that we also tried in our lab setup is how can we attack a power substation? So in a typical power substation, this is a structure where we have process level, quite a few switches and breakers, Ethernet switch connected to the bay level, and finally to the station level with this Ethernet switches. So what you see in most of this is some switch ID or breaker ID. So these IDs are nothing but microcontrollers which are programmed to serve certain purpose. So we picked up a particular breaker ID. So the breaker ID, like you see here in this breaker ID, it comes with a built-in curve, and this curve is pre-programmed. What this curve tells is whether a particular current line is observing overcurrent or undercurrent. Now, when you have overcurrent, if it is a spike, then you can ignore. So this was probably some miscalculation, or this just happened because of some electrical pulses that can be ignored. But if the overcurrent is persisting over a certain duration, then we have to take it seriously and immediately break open the circuit. So this is what this curve is about. So if the amount of overcurrent is small, and if it is for running for a certain time duration, then we know that you can ignore it. But if the overcurrent amount is also large and it is for the longer duration, then we have to break the circuit. So while this curve is fit in the device, what we did is we took an example IED, which is an ARM microcontroller, and then it has a programmable power supply, which is connected with the host computer. In this case, the host computer is acting as an IO, which would be connected to some Ethernet switch. So what we could do is we took the ARM microcontroller and we ran some fault injection, which is basically a side channel attack experiment on top of this microcontroller that could forcibly change the curve. So if I change this pre-built-in curve, that means even though it is overcurrent for a long while, it will think that it is okay to have this overcurrent because the built-in program, it just shakes the current value with whatever you have in the curve. So if the curve itself is wrong, it will run the overcurrent for a longer duration, and then it will cause the circuit to be clearly damaged. So there are plenty of examples of attackings on the unmanned aerial vehicles or this power substation. So what this shows is there are new kinds of attacks, new attack surfaces in terms of spoofing or side channel attack that those were not considered when people designed this smart grid stations or designed this autonomous unmanned aerial vehicles. So what can we do about it? So what is happening right now is security as an afterthought. So example of this is if you look into the microprocessors that we have now in the market, you will probably follow that in the, these are actually coming in the major news, that there are quite a few big vulnerabilities that have been identified in most of the general purpose processor that we see now, specifically whenever they are running something speculative, like the memory access, like the branch prediction. And whenever some speculation is involved, we know that it can be leading to some privilege escalation or reading some secret parts of the memory. And as a result, what we are trying to do is we are completely shutting down the speculative execution parts, or we are creating different segments of the code where we say, okay, if I'm entering into a sensitive area of the code or the data, then I will block the speculation. I will not go for any branch prediction. So this can be countered by coming up with a secure and lightweight processor. So that is what we are doing now based on the RISC-V instruction set. So there are quite a few groups around the world, and some commercial offerings are also coming in this way, where we go for a secure storage, isolated execution, secure boot mechanism, and built-in keys with device identification and authentication purposes. So this is what we are doing because we realized that the way processors were designed was not with security as a architectural constraints. Security was not the prime feature that everyone was trying to optimize. The same problem happens when we look into any edge device. So if you right now buy something like a Raspberry Pi board and you connect this with a camera, this is a simple camera module that is there for a lot of camera vendors that you will see in the market, including the High Logic or Ambertronics. They are selling Ambarella. They are selling this kind of boards and the cameras. And if you again follow the news, you will see that on day-to-day activities, there are plenty of security hack that are happening on such device. So what we can do is we can, like we did in this particular experiment, we had a built-in logic encryption that is capturing the data, and the encryption and decryption, the encryption part will happen at the edge device itself. and then it will send the data to the server. So this is something that we are trying to achieve with an end-to-end encryption. So of course, before we do this, we have to take care of how the keys are generated or how the private keys are exchanged and set up before we do this. So this is, again, we are buying something from the market. We know that the security was not considered when designing this, and we are putting security on top of this as an afterthought. But what we can do is, if we think of security as a design principle, so starting with the design itself and considering security as a layer from the very beginning. So in order to do that, it is important to understand where from the security lapses are coming. So considering a typical cyber physical system, you can segregate that into some separate domains, that we have a sensor and actuated domain, and then we have computing, storage, and communication. So for each of these domains, we know that there are some possible vulnerabilities. And these domains are also possible to classify as some part in the cyber system, where it is relying on a software or a hardware, part in a server or in a communication media. On the other hand, there are some physical parts which is actually interacting with the real world in terms of the sensing and the actuating. Now, this sensor and actuator, inclusion of this brings in additional challenges, because when we were considering the prior generation of CPS systems, which could be extremely large, like a manufacturing plant, water purification plant, or an industrial control system, it did have the sensors and actuators, but everything was within a secure perimeter. Now, when we are thinking of an Internet of Things, this perimeter is gone. That means if I am creating a smart grid, which is connected with a smart home that is generating its own energy through a solar panel, then I can have the sensor just lying on my roof, and I can have some actuator that is connected to the smart meter at my home. And these things are not protected by a secure perimeter. So there is no authentication, no guard, nothing. So traditionally, these things were belonging to the domain of OT security, or operational technology security, and the cyber systems, computing, storage, and communication, they did belong to the IT security. With the advent of CPS and IoT, this OT and IT securities need to be considered together. So we cannot say, I will prevent this system because it is heavily guarded by some person, because it's an access control. So to do that in systematic way, there is a concept of security management that comes actually from IT security, which takes the whole security design through multiple layers. And how these layers to operate, that we have some security standards, which starts from security review up to security accreditation. The security standards could be FIPS standard, FIPS standards. It could be some standard initiated by NIST. Recently, Singapore government also started a cybersecurity standardization scheme, where there could be multiple cybersecurity levels, depending on the particular device or system that you are trying to sell. You need to meet certain levels, so that within that particular standard, you can go and you can convince the users, that the lay user, that this meets a particular standardization. On the other hand, we have the security technologies. It could be software level like firewalls, and then it could be private public interface with the crypto mechanisms, authentication, transaction security. So the security technology and security standardization go hand in hand, where when we go for the security management, it starts from the security objective. So of course, if I'm designing a mouse like that, I'm playing with this mouse, I will probably not go for an ultra high security, because it is closely interacting with the desktop that I have here. On the other hand, if I'm going for an autonomous vehicle, I need to clearly know what are the security objectives. This translates into security requirement, the corresponding risk analysis and assessment, and how do we plan to do the risk management and control. That translates into security designing and planning, finally going to the security implementation. So this bottom-up security management, that is very customary for large-scale system design, and now it becomes part of any CPS or IoT system. So if I go for a security by design principle, then we try to outline several levels that we start initially with, which stems from the confidentiality, integrity, availability triad, and specific aspects of this can be focused depending on the application requirement. Like if you are thinking about vehicle to vehicle communication, then anonymity is an important consideration. Once the security policy is in place, the next thing is that we are talking about cyber physical systems and IoT. So the internet backbone or the communication backbone, it has to be designed with the proper security consideration. So what is my security perimeter? What is the bandwidth? Do we have to secure the air gap or not? What are the network interoperability? So if I just take a particular network which has transition from say Zigbee to 4G, are we considering enough security mechanisms to make sure that this transition from Zigbee to 4G or 5G is also having its own security layer? So there could be overheads that are coming because of the security that we're adding top of the network. Are the overheads acceptable or not? And most importantly, whether we are having a network with well-defined security perimeter. So if I am putting a car, we need to define that whether an attacker, so that's the attacker model, can come close to the car or not. If they come close to the car, they can probably just break it in. And if they break it in, then we don't have to think about all the security mechanisms with different information channels. But if we assume that it's physically protected up to certain range, then we have to make sure that there is no wireless or there is no remote access channel that is breaking the secure network for this particular vehicle. So once we go to the security policy and the secure network, then the next thing is, of course, the secure component. That this whole system is built using different storage and computing devices, sensor devices, actuator devices. Do we have enough security consideration in place while designing individually each of them? So how do we protect the sensor from spoofing? If we have a computing or the storage device, are those leaking some kind of information? So is it easy for some attacker to just pick the information and recover the secret key, which is the whole basis of the side channel attack? And finally, when we go through these three levels, then the last will be the security auditing, which could be done through auditing services, dedicated surveillance technologies, and white hat attacks, crowdsourcing this, security simulation and emulation that has to be picked up. So right now for many designs, like if you're talking about an autonomous vehicle, we know how to design a car and there are plenty of software and simulation environments available. But are those simulation environments capable of running security checks or not? So this is an add-on that we have to consider on top of it. Security auditing, that is not only what we do for the design time, but it translates into a security management because the auditing needs to be done from time to time, like after the car is serviced or it is gone through some kind of repairing or exchange of some components inside the car. So here are some very preliminary results that I would like to share with you. So this is a simulation environment that we are now preparing for an automotive based on the Canoi simulation setup. So this is one of the standard simulation platforms for automotive where you can add many different ECUs which are connected to the CAN bus. And what we could now do is we can keep on reading the CAN statistics, the traces, the data, and see what kind of attacks we can simulate onto this platform. So this is a highly scalable network. You can model a complete automotive in that. And one of the attacks that we could try, it's a very simple attack, is when one ECU, that is one of the microcontrollers inside a car, that went rogue. That means we have some Trojan issue or this is a malicious issue. And what it does is it can read one of the addresses of the ECU, let's say the ECU2, and then starts communicating with the ECU1 by spoofing the address of ECU2. So this is a simple sequence diagram which says that I can use the ECU3 to modify and alter the communication between ECU1 and ECU2 because all of them are accessing the single shared CAN bus. And there is a more involved setup that we are now trying to create is for actual emulation of this kind of automotive network. So the setup that we have here is to model the TLS 1.3 handshake happening between a system on chip environment, which is in this case a Zinc platform, with an HP Core i7 that is acting as the TLS server. So the OS that is running on the Zinc is an embedded PETA Linux that is typical of the automotive environment, and OS on the Intel Core is Ubuntu 16.04. The communication interface that we had to heavily modify in order to suit the needs of the automotive communication is, instead of just running the Ethernet and TCP IP stack, we created the TLS over CAN interface. So this is what was written as a future work for just a couple of weeks ago. We actually ported the full CAN interface over the TLS. And the implementation that we took from the TLS 1.3 is OpenSSL. This is the corresponding version taken from Open Quantum Safe project. So the advantage of OpenSSL is we could modify the different components of the SSL layer, like we modified the CAN interfacing here, and also we could replace like the RSA or elliptic curve crypto systems with recent primitives like post-quantum cryptography. So one of the ideas and goals of this particular project that we are doing from funding from a major automotive vendor is to check how much overhead we will have if we replace the current crop of public key primitives like RSA and ACC with post-quantum crypto primitives. So this is running the Ethernet over TCP IP or Ethernet over CAN bus between a TLS server and TLS client, which can model multiple levels of root certification, which can go on with 2 level of handshaking. That means the server is validating the client and client is also validating the server. And this is the practical setup that we have here, whereas the TLS server that is mimicked by a laptop here is talking with a TLS client. So this shows that we can start with a security policy definition, and then we can have a security simulation interface, security simulation through the Canoe simulation platform, where we can start adding small and small attack examples and see how to modify the existing infrastructure to defend against this attack. And then it can be directly translated into an emulation platform where we have a client server complete protocol running for an automotive infrastructure. So this is actually helpful if we go one level deeper. For example, if we are talking about the different kind of side channel attack, then what we created is our own customized recipe that is capable of running quite a few different side channel attacks and fault injection attacks on a microcontroller. So currently this is capable of running the side channel attacks on Atmega microcontroller, but we have some other versions also, which can also port the attacks on different other processors, including ARM processors. So we can adjust the amount of fault that we want to inject, and a large number of single multi-bit faults can be done. So this is connected to the USB serial port, so you can have your own measurement board that can run the fault injection setup and measure whether we are able to disrupt the complete service or not. So this kind of PCB for a particular board can be coupled together with the Zinc board. So that means you can have a fault injection or side channel listening board, that's an add-on board besides this, connected with the Zinc board to give us the complete setup for the different attack scenarios. And this is a more involved setup that we have where we want to inject the fault or we want to listen to the electromagnetic side channels through external probes. So this is a probe setup on a very simple desktop that is connected with an oscilloscope that can listen to this electromagnetic emission. In this case, it is running on an ARM Cortex M4 setup. And there is a complete fault setup that can generate the electromagnetic pulse. So through electromagnetic or laser pulse, you can create a fault and you can directly see if the fault is affecting the system execution or not. So as you can see from both of this setup, on the side channel or the fault attack setup, they are pretty handy. So in this case, it is coming with a large oscilloscope, but we have another setup where we don't need even the full oscilloscope, but we just have a simple and small measurement board that's almost like a portable oscilloscope. So this kind of setups are now available for pretty low cost to the attacker who can attack any CPS and IoT setup. So we need to know, are we defending enough against these attacks or not? So this gives us the full purview of a security by design principle and a setup for simulation and emulation of these attacks for practical systems. So to summarize the talk, that we already see that the CPS and IoT security, it brings a new set of challenges. Most importantly, we are seeing an overlap of IT and OT security. So there are lots of small devices which are vulnerable. There are lots of heterogeneity in the communication protocols that are not easy to deal with when you want to have an end-to-end security or encryption. And most importantly, security was not considered as a primary design objective when many of the legacy systems were designed. A prime example is large-scale manufacturing plants where forget about security. In many cases, they are not even digitized. So when we are moving towards their digitization and we have themes like Industry 4.0, then security needs to take a prime spot so that we can cover the entire horizon and make sure that we are not caught with surprises. So this will be a real challenge if we have a critical infrastructure like a smart grid or a water purification plant that we rely on from day to day is suddenly falling prey to a cyber attack that we don't have any clue about. So security by design, these methodologies are evolving. So we did some preliminary work and we are currently focusing a lot on automotive. So there are quite a few funded projects that we are running. So these are the ongoing works for security by design for CPS with a focus on automotive. Secure processor design, this in itself is a big challenging project where we don't only cover the processor per se, but we are talking about the servers, embedded systems, embedded processor, all of which they see a lot of cyber attacks which were not even imagined. So this requires us to completely overhaul the processor design and check across all the abstractions, starting from the OS down to the individual transistors and devices where the security leak might happen. And when it comes to the cryptographic standpoint, there are two major initiatives towards standardization that is running now, and we are participating in both. One is to come up with a side channel attack resistant lightweight cryptography. And there is a standardization effort run by NIST that is happening for lightweight cryptography. A lot of candidates are proposed. And the other one is a measure where we are trying to migrate from the existing public key infrastructure based on RSA and ECC to a set of post-quantum cryptographic primitives where we kind of take a precaution against the growing power of quantum computers. And we are taking part in this by benchmarking a lot of NIST PQC candidates for automotive protocols, as well as their plain hardware implementation of this NIST PQC candidates. Of course, to make it again resistant against side channel. So with this, I would like to conclude the talk. And of course, I am extremely thankful and happy to work with a set of brilliant students, many of which have gone on their own paths. And thanks to my collaborators, many of whom are actually mentioned in the papers that I was referring to in the slides. So thank you for your attention. I will be happy to answer the questions that you have now.
Yeah, thank you. Thank you, Anupam, a lot. Yeah, so I guess the floor is open for questions from everybody. Yeah, Chadlia.
I think Amin has a question.
Okay.
Right, he's raising the hand, so you can unmute yourself and just ask the question.
Hi guys. Hi Anupam.
Hi.
Thank you very much for this very nice talk. So I was like following. This is really exciting, and I actually like the slide where you presented the different domains, sensing domain, actuator, then communication part, the cloud, etc. And this is like presenting pretty well what is happening with new systems where we need to offer an end-to-end security. And my question is, I mean, is it enough to secure all these parts independently to say with the high confidence that the end-to-end security is ensured? And yeah.
So this is a very nice question. Actually, definitely, it's not enough to secure all of them individually, and more is the full system is definitely more than the sum of their parts. And the big challenge that comes into is the protocol that is going to be run on top of all this. And I didn't talk much about it because this is not my research domain of expertise, but there are quite a few people who are working on protocol level security validation, where you can actually mention some security properties and see if something in the protocol is violating those properties that you start with. So this was done in the previous generation for CPS safety, where you can have a safety protocol. But the big difference between a safety protocol and a security protocol is, in a safety protocol, you assume the system can go wrong because of some accident. But for a security protocol, the system can go wrong because someone is trying to violate the properties and cause a damage to the system. So that has to be built on top at first. And then the protocol level security tells that it is sufficient to have some security in the sensor and some security in the communication. So you are distributing the security measures across all these levels so that you are not going for an over design or under design. So this is pretty complex to think from the whole systems point of view, but recently in last year date, we published one paper that came out of our DAGS tool seminar, where a lot of people from different areas of security we gathered, and we particularly looked into the security of a digital system, or let's say processor, and we talked about exactly this notion of, can we compose security from the building blocks to guarantee security for the full thing? So it's composable security.
Okay. Yeah. Can you please maybe refer us to this paper so that we can have a look?
Definitely. So maybe I will just follow up with this and I will share the paper link with you.
Okay, thank you very much.
Yeah, welcome.
Yeah, Anupam, so I'll just jump. I don't see any other hands raised. I'll just, I have a question. So I'm very interested in your work on emerging technologies, of course. And so there's memory stores, also quantum computers, maybe also non-volatile memories. You have here data remainance. So yeah, so what is the, so how do these technologies impact all the security things? Is it, so are you working also into that thing? Like, can you side channel attack a memory store array? Or is anybody, so is it going to get worse, or is it gonna improve?
Yeah, actually that's what happened. So there was a group in Penn State who were working on STT-RAM, not in RE-RAM, and we shared some side channel attack knowledge with them, and it turned out that there are a lot of vulnerabilities, like they are leaking information when you are reading or writing.
Right.
So we quickly identified a lot of side channel information through the current flow. And that is not typical when you, let's say, work with an SRAM.
Yeah.
And then it turned out that they can create a lot of Trojan STT-RAMs very easily. So we wrote a couple of papers at the beginning, and after that, this group in Penn State, they continued working on a lot of side channel attacks on STT-RAM itself.
Okay.
So
okay, so that's
you can easily go on into this domain. And now, if I relate with your expertise, I'm sure plenty of exciting topics that comes from the compiler level security assessments. There are people who are trying to do some compiler optimizations or compiler, let's say, security countermeasures for defending against the attacks that are happening in the general purpose processor. like the meltdown and Spectre attacks.
Yeah. So if you consider all these things, like computing, storage, actuator, communication, sensors, and stuff, and protecting all these things, is that so? What is the overhead of all these security mechanisms?
I mean, probably we don't have much choice because
yeah, I know, but is that maybe going to be a showstopper? So is that going to be like, oh, damn it? So the energy for protection is going to be as high as the energy for functionality.
Yeah. So that's also a very interesting perspective that is actually bordering on the economic side. Yeah. So there is a group here in our School of Computer Science who are working on the cybersecurity attacks, but they are working on the malware and virus level. And they are collaborating with a group in the School of Business, where there are some lawyers who works with the insurance companies and so on. And they're trying to develop a model in how to estimate the cost of a hack, that is a cyber attack. What would be the damage? And what would be the cost of protection? Yeah. So if the cost of protection turns out to be too high, they will rather let the damage happen, and they will pay the corresponding premium. So that's it.
Okay.
But that's a very good point. Yeah, that can happen. That I don't want to over design it. I will rather take it my chances.
Right. Okay. Yeah. Interesting.
Yeah.
Okay. Thank you.
I have a question.
Yeah.
So, you mentioned in the last slide that as an ongoing research, I guess, the use of artificial intelligence techniques for security to guarantee security. So, any idea about what's going on with this regard? I mean, is it at which level are the current works considered?
You mean for the security, different security levels?
I mean, the artificial intelligence techniques that were used for security, is it at which layer in the OSI model, or maybe is it at the physical world, the cyber side? I mean, how can we, where is the contribution done so far?
So for us, when we are looking into the automotive security, if you talk about this particular system, then the first thing that we are looking into is their individual computing blocks, because we know that they have the ECUs, which is most of them are ARM based, and how to make these ECUs resistant against side channel, and what is the overhead that we will have to pay if we are migrating from the current crypto systems to post-quantum crypto systems. So this is the first thing that we are looking into, is the individual computing blocks of the automotive. And there are, of course, many more things that can be done, like looking into the protocol for automotive security. But the thing is, the current automotive systems, they already come with standardized TLS and IPsec protocol. And it's unlikely that they will overnight change the entire protocol by considering the security. But there are some automotive security standardization that are happening right now, where they are trying to figure out exactly which layer should be remaining and where more security consideration need to be put into. But we are not looking into that communication layer. We are just looking into the computing, and maybe in future we will look into a couple of sensors where we try to prevent against the sensor spoofing. So that is one issue that we definitely do face when we are looking into large legacy systems, because they come with a lot of built-in protocols and legacy systems that cannot be just overhauled. Although we talk about the security by design principle, but that can be adopted only when you are thinking of a system design from scratch. That I want to design a robot and I completely take the control of it on how to design it from the very beginning. Then I can do this principle. But when there is an automotive company that comes to us and funds some research, that of course we cannot tell them to throw away all the existing protocols.
Are there any available frameworks for security by design?
Yeah, so this is security by design is something that we are trying to propose for a lot of domains. And we tell that, okay, there is a security management principle. So this is the security management principle that starts with the security objectives. That I want to achieve this much security for my system. These objectives translate to the requirement, and then I do a risk analysis, which translates into risk management, then security design, planning, and security implementation. Now, this whole thing, this is very well known if you now talk into the IT security for, let's say, a defense infrastructure or IT security of a bank, then people do this already. But we do not know how to port this overnight into a CPS and IoT system. And that's what we are trying to do. So if I'm designing, if I'm designing smart healthcare, right now, we don't start by defining the security objectives, but that's what we are telling, that you should start by doing that, because that is an important design criteria that you cannot miss. You cannot have security as a afterthought.
But Anupam, if I may, doesn't this like asking people to apply some security standards? I'm thinking of the ISO 27001. So, am I right?
Yeah. But the security standard, they are also facing some issues because you cannot have an uniform standard across all the domains. And we see the proliferation of CPS and IoT in so many different domains. So they have their own safety standards, but they need to translate and link their safety standards with the security standards.
Does it make sense to have a particular language? I mean, if I recall from Geronimo, he talked about domain-specific languages, a language that will enhance and make sure that security isn't there, maybe with basic building blocks in it. Of course, it depends on the domain, on the target domain, but I don't know if both of you think that it could be something interesting to have.
So maybe so I think that's very interesting. So I think Anupam mentioned the difference between safety and security. So far we've worked mostly with safety, like from the semantics of the domain specific language, you can ensure that some things will not happen. And the thing is, some of the safety issues also open security holes, right? Like buffer overflows and this kind of things. So with languages we've shown, but for very specific purposes, that you can protect against those safety things. Also, we work a little bit on DSLs for formally verifying protocols and stuff like this, like that, because I think that's also like another interesting thing. So you have languages with which you specify things, and if the language is formal, you can formally verify that what you have specified is actually working. Exactly. And this is some work that we did with Thorsten Struve, who was a professor in Dresden for security, now in Karlsruhe, and that was an interesting project, right? Like really showing that some of the things that have been attacked in the past in TCP/IP stacks can be prevented if you have like as Anupam was saying, like secure by design kind of synthesis of the protocol implementation. So that's also something that we've worked on. And so we have been doing some studies of DSLs for, and I think Anupam also knows this thing, this homomorphic computing, right? So and deciding from the language point of view, deciding how to protect data, but that's just initial work, not published. I think that's a very hot topic as well. And I think the interaction between these layers is a very interesting and also challenging research, right? So what you do in the language, what you do in the system, and how these things can bring to synergetic effects, right? But yeah, so I'm just scratching the surface here. I think Anupam is more an expert in this field. So I guess Anupam doesn't. You don't want to add anything? You're just being kind, and you don't want to correct me.
No. I think you covered the spectrum pretty well. Yeah, and there is at least one more that I know where people are trying to formally specify the security properties and also formally verify it. So this opens up like in the prior domains where we were calling it functional verification, or functional testing. Now we can specify security properties, and this is security verification, security testing. And this is already being done for at least processors. So you can design security properties, and you can, like the buffer overflow attack, that you can prevent by saying, I have this property.
Can we say that it's enough to have it at the language level, while attacks just appear, new attacks appear every day? I mean, it's sometimes it's hard to get into the shoe of the attacker and imagine new scenarios, and language or frameworks that have been developed so far will only take into account the previous, the already known scenarios. So, anyway.
This is a very general problem with cryptography and security, that you are as secure as the all known attacks. And tomorrow there is a new attack that can emerge, which we have no clue about. So the only way to is keep on doing a lot of white hat security testing and maybe offering bounties. And this is what's being done. Earlier generation, it was being done for all the software systems and IT systems that people were offering, like Facebook and Google. They offer bounties if you can break into their systems. And now this is happening for even the car vendors, that they offer small workshops where you can go and try to break into their cars. If you can do that, they reward you with some money. So this is promoting a lot of white hat attackers to continuously test the system. But if there is a new attack coming in and this is not released, and this makes way into some bad guys, then the system is vulnerable. Yeah. So you can formally claim to have the security up to a level, but when it comes to the security of the physical thing, like the side channel attack, or you just go and you cut a wire or something like that, so there is no formal guarantee, right?
And yeah, one more question. Sorry.
Sure.
So I'm also thinking of like these attacks where the attacker tries to alter the environment, not directly the system itself. And here I'm thinking of the example of autonomous cars. So basically, they try to rely on some cameras, trying to understand the environment, and then decide what should be done. And then there are some models. I think they are called adversarial models, if I'm not mistaken. And the thing is, like, they try to put in front of the cameras an image that would be for sure be mistakenly interpreted by the AI algorithm or whatsoever, the control algorithm, and then leads to some wrong decisions.
So what you are referring to is adversarial attacks for machine learning.
Yeah, exactly.
That is entirely a new area. Entirely a new area. I didn't even touch it, because when you are making your system more smart and you are making a lot of decisions based on the neural network, which is trying to do some kind of classification or prediction, you can fool it in again a lot of different ways. So this is something that we again wrote a survey paper on all possible adversarial attacks. And we are trying to currently look into some sample problems on where we map a neural network on a very small device. Then we try to do a lot of compression, right? So this is one of the common things that people are trying to achieve, small ML. One question that we're trying to figure out is, when we are compressing, are we also making it more vulnerable? Is it easier to attack? Yeah, so we have some preliminary results in there, but I didn't even touch it because that would make it like grow in one domain. So So it's AI security itself is another issue. But the idea is same, that we are making the system more connected and more autonomous. That definitely brings in a lot of challenge in security.
Mhm. Thanks, Anupam.
Yeah, yeah. Welcome.
Okay, so I don't see more hands raising. So I guess thank you again, Anupam, the name also of the rest of the attendees, and maybe we give you a a virtual clap. Let me see how, yeah, exactly that. Thank you, Anupam.
Okay. Thank you. Thank you.
Have a good night over there. Yeah, thank you everybody for attending.
Thank you.
Okay.
Bye.
Have a nice week. Bye.